Professor Mahendra Singh sir to give a brief description about the lecture series which we conducted so far. Sir, as we have the last lecture, so I would like to request you to speak few words on the lecture series.
Okay, thank you very much. Am I audible?
Yes, sir, you are audible.
Okay, at the outset, many thanks, Professor Boulanger, for being with us. This is a lecture series which is being conducted by our student chapter. It is called as Indian Geotechnical Society Roorkee chapter. So Indian Geotechnical Society has almost 52 chapters across the country, out of which Roorkee chapter is one chapter, and we have our own student chapter. So they are quite active, and you'll be happy to know that they started in June, and yours is the 7th lecture which is being organized. And you will get the idea that the first lecture was by Professor G.V. Ramna from India, NIT Warangal. Then second lecture was by Professor Stavrola Konto from University of Patras, Greece. Then third lecture was Professor Jonathan Napet from University of Dundee. And fourth lecture was by Professor Mikhail Brown from University of Dundee. Then fifth was a technical lecture by Mr. Kedar Berit. He was from a firm. And then sixth lecture was by Professor Shridesh Dashti from University of Colorado. And today we are concluding with very, very important topic by Professor Ross W. Boulanger. So these are the activities which the student chapter has done, and I would like to congratulate my young students who are conducting these activities. I forgot to tell about me. My name is Mahendra Singh, and I am here in the Department of Civil Engineering at IIT Roorkee. Currently, I am the chairman of the Roorkee local chapter, and I have here with me Professor Samadhya, who has been the IGS, Indian Geotechnical Society National Society President. And also I have with me here Professor Vishwas Sawant. He is from the Department of Civil Engineering. And our head of the department was here. He had to go, so he has sent his apologies. So with this, I request the organizers to go ahead with the proceedings.
Sir, now I would like, we are having Samadhya sir with us, so I would like request Samadhya sir to say a few words about the lecture series and the activities which are being conducted by us.
You are muted, Professor Samadhya. Unmute yourself.
Professor Boulanger, welcome to this lecture series. Now, as Professor Mahendra Singh has already said about the Indian Geotechnical Society, it is a very active society, and out of 50 odd local chapters, we are one of the most active, you can say. Last year, we have organized Indian Geotechnical Conference at Roorkee, and student chapter, they have organized various lectures. This apart from this lecture series, but during the COVID period, they have organized many lectures in which many speakers from abroad, they participated. So I would like to thank you from the department side that you have agreed for the request of our student chapter. So we welcome you, and hope that all the participants which are attending this particular lecture, they will get benefited, because you are the person whose method almost all over the world we are following for the earthquake resistant prediction.
Yeah.
So thank you so much for joining us.
Well, thank you. Thank you very much. Yeah, the student chapter you have is very impressive. I had the good fortune of visiting Roorkee a few years ago, It was great hospitality. I really enjoyed the event. And when the students reached out and asked if I would participate, I was more than happy to. I think it is wonderful they have the initiative and have taken the leadership to put on these kinds of seminars. So yeah, thank you very much for inviting me. And on my end, I'm sorry I didn't check the time zone difference either, but it's easy to get confused on these conversions. And thank you for shifting a little bit so we'll get back organized. So shall I dive in?
Sir, wait, we'll ask now V.S. Avan, sir, to give a brief introduction of the speaker.
Hello. So, good morning, Professor Boulanger, and good evening to all the other participants. First of all, thank you, sir, for accepting our invitation and delivering the lecture here now. It is my pleasure to introduce expertise like Professor Boulanger from UC Davis, whose pioneering contribution in the field of liquefaction is well accepted by all national standards. Okay. So Professor Boulanger is a consulting civil engineer and Distinguished Professor Emeritus in the Department of Civil and Environmental Engineering at University of California, Davis. He received his bachelor degree from University of British Columbia and then followed by the master's and doctoral degrees from the University of California at Berkeley. His tenure at UC Davis from 1992 through 2023 included 14 years as director of the Center of Geotechnical Modeling and its national shared use centrifuge facilities. He has over 300 publications primarily related to the area of liquefaction and its remediation, seismic performance of dams and levees, and seismic soil structure interaction. His consulting activities are primarily related to the dam, tunnels, and infrastructure projects. His honors include the Casagrande Award, the Huber Prize, the Norman Medal, and Peck Award from ASCE, the Ishihara Lecture from ISSMGE, and election to the US National Academy of Engineering. So with his very brief introduction, I request Professor Boulanger to share his wisdom. Thank you, sir.
Thank you. Well, I'll see if I can share the screen now successfully. Are you seeing my screen properly
Yes,
now?
sir.
Yes, sir, it's visible.
Yes, sir.
Oh, thank you. Thank you. Okay, well, thank you very much again for the introduction and for the invitation. Again, I'm very impressed with the activities of the student club, and I'm happy to support in any way I can. So it's your evening and it's my morning, so I'm going to see if I can walk through this talk fairly efficiently. What I've chosen to talk about is a lecture that I gave earlier this year for the International Society in Osaka, Japan, at our ISSMGE conference. And this is a lecture I was very fortunate to give. It was the 9th Ishihara Lecture. And the topic is the effects of the subsurface heterogeneity on the liquefaction effects that we see following earthquakes. Now, as the Ishihara Lecture, let me get this screen. There we go. I wanted to first acknowledge Professor Ishihara, who is shown over here towards my laser pointer. This is Professor Ishihara. And Professor Ishihara is a past president of the ISSMGE and one of the founders of the Technical Committee 203 on Earthquakes. And this is from one of our conferences in Vancouver in 2017. If you haven't read many of his papers or his book, I really encourage you to. Seminal writings, strong influence on all of our work. And in addition to his technical work, all his leadership in the International Society has really helped build communities, much like your student chapter is doing by these types of seminar series. So it was very much an honor to be able to give this lecture in his honor. I also want to start by acknowledging a few people. In particular, this group shown here, starting on the left, it's Patrick Basal. And Patrick is a former PhD student who co-authored the paper that goes with the Ishihara Lecture with me. And if you wanted to get a copy of that paper, you can go to my homepage at UC Davis. There's a tab for publications. We're not allowed to post PDFs openly. So what you can do is click on a little tab only for friends, and it's password protected, and the password is friends. And if you go in there, you can get a copy of the Ishihara paper that I'm about to present to you. And then I also want to acknowledge the other 4 people here, Nick Paul, Jack Montgomery, and Sean Munter, our former students whose work are going to be heavily referenced, working with myself and my colleague, Jason DeYoung. Now, stepping back and for the context, we've been working on liquefaction problems for over 50 years. And we've really made advances since the 1960s and 70s. We've got advances in how we characterize seismic hazard, how we characterize sites, the analysis methods we use, the way we remediate sites, how we evaluate risk and make decisions. And so we've gotten better at almost everything, some really tremendous advances. But if there's one place where we get in trouble with liquefaction evaluations, it's by not having a good enough quality site characterization. And so really the quality of any liquefaction study really hinges on doing the site characterization well. And that has always been kind of an interest of ours to look at aspects of that. Now, when we look in the subsurface, heterogeneity is at all scales. So it exists in many forms. We see it all the way from particle scale, which can influence the fundamental behaviors of soil, like we might study with discrete element methods, and move up to the size of beds, about the dimension of a meter, say, where it's about the volume of soil that we measure with an in situ test, CPT, SPT, or say certain shear wave velocity techniques. Then you move up to a project scale kind of in here where you've got the size of a dam, a bridge, some infrastructure project. And then you move up to regional scale where we're doing emergency planning, regional loss planning. And when we look at heterogeneity at these different scales, we have different issues and concerns and details to address. For this lecture, what we're focusing on is those middle two. We're at the project scale. And when we look at things at that scale, we can take the heterogeneities and we can treat them in 3 categories for practical purposes. And those 3 categories are stratigraphic heterogeneity. These are the large scale differences that come from formational processes. Or within those large scale stratigraphic units, we can look at lithological heterogeneity. And this would be within a unit where there's the persistence of distinct interlayers, like interbedded sands and clays, or gravels with sands, things like that. We also have inherent soil variability, where maybe within a unit it's a fairly uniform deposit of clay, but you get local variations in undrained shear strength, or in a deposit of sand, you get variations in relative density. So if we look at those 3 forms of heterogeneity, stratigraphic heterogeneity is something that we currently and generally do deterministically. We look at our in situ and our geologic data, and we interpret the subsurface major units. There are emerging tools to help us do that with machine learning and other types of tools, but in general, we still do this mostly deterministically. When we look at lithological heterogeneity or inherent soil variability, we have a number of stochastic tools. Now here we're looking at variability that we can't define with sufficient detail. So we use stochastic models to generate the possible realizations that might exist consistent with our data. Now there's a number of tools available, and I list some examples for each of these. I'm not going to be going over these individually. I'm going to use one of each as examples to illustrate some problems we deal with. Okay, so with those categories of heterogeneity, we're now going to take those and incorporate them into nonlinear dynamic analyses, which I will just call NDAs for short. Now, we're going to do this 2 ways. One is we will apply it to specific cases. These will be like case histories or projects where we're applying these tools to. And what we're trying to do is quantify how heterogeneities in the subsurface affect the response of the system, magnitude and variability of deformations most commonly. The second approach is we'll do scenario studies. We'll take idealized representative structures and we'll parametrically examine those to get insights that we can then use to develop more general guidance for more common practice. So I'm going to show you examples of both of those. And with that, that brings me to the outline of the paper. And really what I want to try to do today is motivate you, if you're interested in this, is to get a copy of the paper. And you'll see that these are the main headings. Start with some review of geologic and anthropogenic controls. We'll look at the effects of inherent soil variability first, then the effects of lithological heterogeneity. And both of these will be using scenario studies. Then we'll look at case history studies, 3 of them that illustrate the application on specific cases. There's another one, Paris Dam, which I won't have time to cover today, but it's an application at a project scale, demonstration project. The details of everything that I'm going to do are in the paper. And so I'm going to try and touch on these today at a fairly high level to illustrate what I hope are the key points regarding the treatment of heterogeneities. And with that, I'm gonna then now walk through each of those. So each one takes a few minutes and then we'll get to the end. So the first section of the paper talks about geologic and anthropogenic controls. And really here we're talking about stratigraphic heterogeneity, the major units that we can identify. This is something we've seen many times through case history. And some examples, different scales. The one on the left is a very small lateral spread into a historic channel affected by the Tohoku earthquake. You can see the lateral spreading coming in from both sides. This was very easy to have anticipated. This is a historic channel that crossed perpendicular to this channel. It's infilled with loose fills, and you get this very small localized landfill. So if you knew the history of the site, you knew where these happened all the way along the channel. On the right, all these sand boils in the sand plain along the Tone River, they all coincide with the mapped limits in yellow of a historic river meander from the 1880s. So again, historical records and historical photographs, you would have known where this was. The one on the left is now a much larger lateral spread along the Kaipoi River in the Canterbury earthquake sequence in New Zealand. And here is a very large lateral spread of the boundaries of which coincided with the mapped edge of an abandoned river channel. So again, knowing the local geology and history of a site, you'd know where these problems were going to be. The one on the right is 3 buildings from Adapazari. All 3 buildings are about the same. These 2 buildings on the left had ground failure and punching into the ground. The one on the right did not. And the difference is simply the presence of this shallow deposit of low plasticity silt under 2 of the buildings, but not the third. So over and over again, we see this. Throw in 2 other examples just for some cross sections. They come from Holzer and Bennett. This first one is a very large spread from the Loma Prieta earthquake in California. And the zone of lateral spreading coincided with the zone in red, which is a younger channel sand deposit. And the ground failure just mapped right to the edges of it. And that channel deposit was incised into older deposits of floodplain, clay, and plastic silt overbank deposits. And so these are more plastic materials. And they're very easy to identify the boundaries because you can see within here, the borings, these are granular material sands, the texture, the lithology of them, such a very easy to tell them apart from the plastic silts and clays in the surrounding units. And the CPTs, very low tip resistance versus relatively high tip resistance. So very easy to see the boundaries. And the second lateral spread I threw in is from Heber Road. It's a kind of a medium-sized lateral spread. Again, the zone of lateral spreading mapped to this unit A2. A2 is a stratum of loose fine channel fill sands. It had an average cone tip resistance normalized to atmospheric pressure so 20 bars. And you could tell that unit from the surrounding units. On the west side, this was a much denser point bar deposit where the tip resistances were about 8 times higher. And then on the right-hand side, or the east side, you had overbank deposits of fine sands where the tip resistance was about 2.5 times higher. So it's a little more attention to pick out this unit relative to the surrounding ones because they are sands, all 3 of them, but there are textural differences that you could tell the deposits apart and the difference in tip resistance. And so attention to these details, identifying the major units, they help us find where liquefaction is most likely, both in terms of extent and severity. So the punchline from these case histories over and over again is that stratigraphic heterogeneity, whether it's geologic or anthropogenic, often has a first order effect on liquefaction effects. We see this again and again at different scales. And it emphasizes that an essential first step in any site characterization work is to understand that local geologic environment and review the historical records to make sure you identify those. So that's a key first step. Now, another aspect of the geologic and anthropogenic controls that we discussed is the importance of geologic models for helping us interpret site characterization data. And geologic models, where we try to have a mechanistic description of the processes and their sequence and types that affect how soils are laid down. So we're trying to get depositional, anthropogenic, and environmental processes. And just to illustrate it, this is one generalized model for deposition from a meandering stream, and it points out the types of features you can anticipate in different environments, like the difference between a point bar deposit or a cut bank, anticipating overbank natural levee deposits, the possibility of crevasse splays. They tell you that in the subsurface, the kind of stratigraphy you might expect between overbank and channel sand deposits. And they point out that if you put in borings and they are widely spaced or spaced more widely than the actual subsurface features, then when you connect the borings, you can't actually infer the details in between. So having a geologic model and knowing the sense and scale of features allows you to have the understanding that what you might be missing between your exploration holes. And that allows you to understand what you can get into trouble with. Now, generalized models are valuable even if you can't match site-specific conditions generally. So just like the cartoon, there's others for, braided rivers or fans or glacial deposits, etc. And they allow you to anticipate what you might expect. And the same is true for environmental factors, understanding the age of a deposit, whether it's been over-consolidated, maybe in a degrading depositional environment or glaciated. These types of factors, even though they are not inputs to our analyses directly, they are the factors that affect penetration resistances and cyclic behavior, and they are often the clues for us to sort out what can sometimes be differences between our different in situ test results and resolve and understand them. So understanding those is very important. In terms of interpreting data, I threw one example in for a project. It's an embankment dam in Southern California. The dam is laid over the foundational alluvium in this area. And initially, the explorations, the data was very surprisingly complex in the nature of the materials. And in order to make sense of it, it was really helpful when the engineering geologist pointed out there's actually 4 depositional processes in this environment. There are talus debris fans that have come in off the channels of the valley, and those channel deposits give you sharp, angular, unsorted slates and shales that are coming off the hillside. So they have quite a different characteristic. Then you have a small river, stream that runs through the valley that would sort the materials, so you could get zones where you had well-sorted gravel-sized particles or well-sorted sandy-sized particles. There were overbank deposits which ponded, and you would get lenses of low plasticity clays and silts that were nearly normally consolidated under the weight of the embankment. And then you had flash floods that would come down the valley, mix it all up, and put in thick layers of poorly sorted mixtures of all of the above. Once you knew that, you could look at the exploration samples and sort the data by the different depositional types, assign properties to each of those depositional types, and then talk rationally about how they would behave as a system. Without that, you're just mixing apples and oranges and watermelons and everything together, and it's not rational. So extremely helpful. Now, another aspect of understanding the geology is the scale of the subsurface features, and it goes directly to some of the engineering issues we'll talk about later. Now, I illustrate it here. The schematic shows the same foundation, top and bottom. If you have a small embankment, then the potential failure or deformation mechanism for a smaller structure engages a smaller volume of the foundation. And that smaller volume of soil, when you move along the alignment of, say, that levee embankment or whatever structure you're looking at, the smaller volume of soil is going to have a larger variability in its properties. It might be controlled by the units of individual types of strata or smaller local weaker zones. If you have a larger structure, the failure mechanism is larger and it averages the shear resistance over a larger volume. A larger volume has a smaller uncertainty in its average resistance. And you're going to see this come up in some of the stochastic modeling that we're going to go through. But it's very important, and this applies to whether we're doing stratigraphic heterogeneity, lithological heterogeneity, or inherent variability. Scale of the structure affects how we interpret properties. Okay, so those are just some general points pulled from that part of the paper. And I'm now going to switch and look at inherent variability. And here we're going to do analyses that compare stochastic and uniform analysis models. And the question that we're posing is, how do you select a representative property to represent a spatially variable or a stochastic stratum when we run analyses, particularly when we run an analysis model, like this mesh shown here, where for an individual layer, we're going to assign uniform properties. That's our most common approach. And it's illustrated in this cartoon. If you had this stratum here and you had this range of blow counts, you're going to look at those blow counts and pick a value for which you are going to assign the properties to an individual stratum. So how do you pick representative properties for a variable stratum? And we're going to look at this question by running a nonlinear dynamic analysis two ways. Once where we will model this type of stochastic variability. A second time we'll run it with uniform properties, one particular uniform property for the value. We'll compare these and see if we can get guidance on how to pick those. I'm going to start with some work that Jack Montgomery had done, and it's illustrated in this schematic here, or this drawing. It's a 45-meter tall embankment dam on spatially variable alluvium. We're going to run the simulations, the run with the program FLAC using our PM4 sand constitutive model. And we're going to run them once with stochastic properties, and that's shown with these contour zones. The red zones are going to be very low SBT blow counts. The dark blue are higher blow counts, and the green are in the middle. And then we'll run it later with the uniform model. I'll show you that in a second. Now, if you take all this stochastic variability in the foundation, every element in the FLAC model is assigned one of these gray dots. So these are the individual blow counts for different elements. And you can say they go from single digits up to 30. So it's a big range. The cyan dot is the average at any one elevation. And in fact, for this distribution, the overall average is 15. The horizontal plot is the same thing, except for now the averages are in vertical columns. And you can see the average is about 15 in any one column along the length of the embankment. Now, we do a bunch of analyses with different motions and properties and scales of fluctuation and other stochastic parameters. The punchline stays the same. And so you take all those data in this realization that I showed you, and you rank order them, and you get a cumulative percentile distribution for blow counts. And for that realization, you get one of these blue lines. We run 7 different realizations, you get 7 lines, you get about the same distribution each time. We're then going to run uniform models. And what we're going to do is, for the alluvium, we're going to assign that alluvium one set of properties based on an SBTN value. That is, say, the 50th percentile is a blow count of 15, or the 33rd or 34th percentile is a blow count of 12.5, or the 20th percentile is a blow count of 10. So you'll see those different analyses for uniform models. This is an example. The top figure is a stochastic model, realization number 1. And what you see is, for this particular realization, you can see shear strain contours on the plot. The shear strain contours go along in preferred paths, seeking out the weakest interlayers. And then deformation of the slope is accommodated by deformation stepping up and down into the weaker layers throughout the foundation. And you get, a little over 1 meter of movement at these different points. The bottom model is if you use uniform properties, where the alluvium is assigned a blow count of 15 everywhere. And you see the shear strain contours are now more uniformly distributed because the properties are more uniform. The embankment displacements, crest settlements, are a little less than 1 meter, but these are actually pretty comparable values. You see, we look at how much the upstream slope moves, this is the upstream slope, how much it moves, and how much the downstream slope moves in the downstream direction. And we'll look at those as well. So we get a little less with the uniform model. We repeat that, and that's shown here. This on the left is crest settlement. And now we're going to show it versus peak crop acceleration. We take the ground motion and we just scale it linearly to different PGAs. What you're seeing on here are the crest settlements. The purple dots are from the individual stochastic realizations. The cyan dot is the median of those 7 responses. And then you see these different solid black lines or dashed black lines. This lower one is what you get with a uniform model with a blow count of 15. And you get that one. That's the 50th percentile. This is the 34th percentile. And that would be the 20th percentile blow count. And you can see, if you wanted to predict the kind of the median response, you'd use something between the 30th and about the 45th percentile property. This other graph is horizontal stretch. You'll see this again in a minute, but we take the downstream movement on the downstream berm, we add it to the upstream movement on the upstream face, 2 representative points, and we divide those, add those together, and it's a measure of how the embankment stretches or extends horizontally as it slumps. And you get the same general conclusion that I already showed you. Okay, now we can generalize that, and we can start looking at different size embankments. So 45 meter high, 25, 10 meter, 5 meter high embankments. We can now change the distributions, the stochastic properties, and et cetera, and we'll try to generalize it. And that leads to this figure, which is a little complicated, but we're going to walk through it now. It goes like this. All the figures on the left are showing crest settlement normalized by the height of the embankment. And that crest settlement is from the from the uniform analysis models. And they are all plotted versus, on the x-axis, the crest settlement from the stochastic models. If you look on the top row, the uniform analysis model in yellow is from the 50th percent property. The row below it is if you use the 33rd percentile property in the uniform model, and the bottom is the 20th percentile. The figures over on the right are the same things, except for now they are that horizontal stretch of the embankment. We're going to look at the top row first, and I'm going to point down here at the legend that the X is the blue X is the tallest embankment. And if you look up here, the blue X's are all very close to the 1-to-1 line shown by the black line there. And what that shows is if you used the 50th percentile property, the taller structure, on average, those blue points are pretty close to the 1-to-1, which means the uniform model would give you about the same answer as a stochastic model. As you go to smaller and smaller structures, like the green square is a 10-meter high, the red plus is a 5-meter high embankment, you start to see more spread in the results. And that's because smaller embankments, they could be locally over denser materials or locally over looser materials. So they can move quite a bit less or more depending on the randomness of what's under them. And so you get more variability with smaller structures. But that is about, on average, close to the 1-to-1 line. Now, if instead you wanted to be a little more conservative and you use, say, the 33rd percentile properties, you see that the uniform model with lower properties will all give more movement, so the points just shift upward a bit. And now you see relatively few points below the line. This gives you a more conservative set of answers. Same over here for stretch. And if you did the 20th percentile property, you move the majority of the points over the line, and now you'd be even more conservative. So really depends on what you want to get. So if you want an estimate of median crest settlements or median embankment slope displacements, it would appear from these analyses you use something like the 45th to 50th percentile properties. But if you want to be conservative and you want to say not have your displacements exceeded in no more or no less, say than 16% of the cases, then you might use something like the 30th percentile. And in all cases, what you have to recognize is that a uniform analysis model cannot reproduce the variability that comes when the structure or the deformation mechanism is small relative to the scale of the foundation features causing deformation. And so it's that spread in these red dots, and you can never get that for the small structures. And so here, that's where you might want to consider a range of representative properties to have a sense of how variable the deformations could actually be. And to just kind of conclude that section of the paper, we also go over a review of studies for lateral spreading and reconsolidation settlements. We get very similar findings. And the general conclusion is those scenario studies gave us some guidance on how we would select representative properties in practice when we're doing uniform analysis models. And they also give us some guidance on the nature of the uncertainties in deformations one might expect and should allow for in design or evaluations. Okay, so that was inherent variability. So now I'm going to switch. That was one source of heterogeneity, and we're going to switch to lithological heterogeneity. And we're going to do one example to illustrate this aspect of the problem. And we're going to do interbedded sand and clay seams. Now, when we do interbedded sand and clay seams, there's been a lot of experience, particularly out of Christchurch from the Canterbury earthquake sequence and other earthquakes, that show when we do different one-dimensional liquefaction vulnerability indices. These are when you just take a CPT or an SPT profile and you integrate strains with depth, or integrate some weighted factor of safety with depth, like the LPI, the LSN, the LDIs, etc. Just one-dimensional methods. And they tend to overpredict ground failure when we are in these thinly interbedded sand and clay types of deposits. Now, there's a number of reasons we would overestimate deformations. The first reason is site characterization, and you illustrate that with this photo. And that if you have interbedded sand, silt, and clay interbeds, and they are on the order of just 10 centimeters thick or something like that, well, when you drive a CPT through this material, or you drive an SPT through these materials, the failure mechanism, the tip resistance, engages a volume of soil that is larger than the interbeds. So the tool never measures the property of any one interbed, but rather as a composite smearing of their properties. And that means you never get a good result for any of the materials. And so that's a challenge. Then some of these materials are silty clay sands, and our engineering correlations aren't well developed for those. So there's a potential bias there. And the third is that earthquakes are a dynamic problem. So any spreadsheet type calculation or a one-dimensional non-dynamic analysis method is not going to get the system level effects that Mishko Kubernovsky and others have talked about extensively, illustrating that dynamics can be very important in terms of sequence of what liquefies and how it affects responses. So one example of why that can be important is a study by Munter, and this is a infinite slope model. This is about a 36-meter long segment of an infinite slope with a 4-degree slope angle. It has a 3-meter thick crust layer over 6 meters of interbedded deposits over a stronger base layer. And what we're going to do is we're going to generate for this model realizations that have sand interbeds in a clay deposit. So like a small meandering stream into a overbank clay deposit, for example. And we're going to generate realizations using a transition probability-based indicator geostatistics program called TPROGS by Carley and Fogg. And we take those realizations and we run analyses using FLAC with PM4 sand for the sands. Now what happens is on this top figure is a case where the percentage of sand, referred to as the sill, that percentage of sand in the deposit is 20%. That means the pockets of sand are isolated, which means if you shake it during an earthquake and you want to get lateral spreading, we need to develop shear strains, like shown on the right, that cut across both sand and clay. Has to go through both materials. The middle row is if you have 40% sand and the bottom is 60% sand. If you get to 60% sand, you can draw pathways across the sand layers where the shear bands or shear strain contours that go through that deposit, the majority will be stepping in and out of sand lenses, and you get less and less clay being involved in the deformation mechanism. And then you parameterize it and you get the result shown here, where this is lateral displacement of the slope versus the percent sand in the stochastic model. We start over here on the right. If you have 100% sand, it's just a sand layer. For the example ground motion we're showing and all the various conditions, you get a little over 1.2 meters of displacement. Then each of these curves coming down is as you reduce the amount of sand, and these colors here for the different points are increasing the undrained shear strength of the clay. And what happens is if you have, stiff or very stiff clay, then these displacements come down very rapidly. And by the time you get below about 40% or maybe 20% sand, if the clay is strong enough, we get very small slope displacements. If the clay is very weak, then a very weak or very soft clay, then even if you have very little sand, you can still get strains developing in soft, weak clays. So just because it's clay doesn't mean it's not a problem. It just might be a different problem. The punchline of this is that lateral spreading decreases rapidly with the decreasing sand proportion and with the increasing undrained strength of the clay. That the horizontal displacements, they're controlled by the clay when you get down less than about 20% sand. And that's because for these examples, the mean length of those sand lenses was small relative to the length of the slope. So it's always got to be in the context of how large the geologic feature is relative to the structure. And it just illustrates again that the composite response of these deposits, it depends on the properties of both the sand and the clay and the connectivity of the sand interbeds over the scale of the structure you're analyzing. And that again is where geologic models can help inform your judgment as to how large those features might be. Okay, so that was an example of a scenario study for lithological heterogeneity. And then I had 3 case histories to walk through. Palinurus Road, I'm gonna watch my time here and see if I can get through this fairly quickly. So Palinurus Road, it's a site from Christchurch. It's an open sand, grassy field, sand boils on the north, no sand boils on the south. The question was why the difference? One-dimensional simplified analyses do not tell any difference between these two. So this is an area of fluvial, estuarine, and swamp deposits, Holocene deposits to a depth of about 16 meters. And here we're sourcing all the data from the New Zealand Geotechnical Database. These are the CPT profiles. The yellow is just showing we have lots and lots of sand. The orange on top is another unit of sand. This zone in pink is where you get thin interbeds of silts and silty sands. And so in this region, these estuarine deposits, swamp deposits, we're getting these interbeddings of silts that give you lower vertical hydraulic conductivities. So they're interbeds that lower the permeability. And we're just going to model this, the simplest case, as a stratigraphic heterogeneity. So this is the FLAC model, again, using PM4 sand, and this time PM4 silt for the silt. And we just model it with uniform properties. We vary those properties. The punchline stays the same across all the parameter variations. One example result here, these are pore pressure ratios in the top. You see we liquefy all the sand. This dark blue is 100% pore pressure. We don't liquefy the sand over top of this lower permeability silty sand interbed zone. I'll explain that in a second. Maximum shear strains, get similar strains north and south. So lots of liquefaction north and south. What happens is high pore pressures, you get an upward hydraulic gradient, water flows to the surface. On the south side, that water tries flowing to the surface. It can't get through these silty sand interbeds, and it's easier for it to flow laterally and come up over on the north side of the field. Because water is not flowing upward into the zone, the overlying sands don't get refreshed with upward flowing or inflowing water, and so they never quite generate as high an excess pore pressure and don't trigger 100% pore pressure ratio. And that's summarized in this figure. A few things going on here. This is X is the position along north-south in the model. This black line is about the edge of that subsurface silty sand stratum C1. No sand boils on the south. The sand boils were all on the north. And what we're going to plot on here are post-earthquake settlements and water flux. Now, water flux is going to be all the dashed lines. The water flux is volume of water per area, surface area. If water comes out to the ground surface in a certain volume, the ground has to settle. It's just conservation of mass. So over here, these dashed lines show that you get about 6 or 7 centimeters of water come to the surface. If 6 or 7 centimeters of water come to the surface, then the displacements out of the solid lines, they are eventually 6 or 7 centimeters as well. So away from, like far to the north where things are very one-dimensional, volume of water coming out equals settlement. On the south side, where there are no sand boils, you get very little water comes to the surface because it couldn't get through the silty sand layer. But the underlying soil is still liquefied and they still reconsolidate, and you still get 4 centimeters of settlement computed a long time after shaking. So these are all the lines are at different times. So right past the edge of that C1 stratum, water on the south side is flowed towards the north, comes around the edge and comes to the surface there, and you get about 20 centimeters of water come to the surface. The ground settlement is still only on the order of 6 centimeters. And what's happened is the water from the south side comes around that stratum, exits the surface, and that higher flux of water is going to accentuate the formation of sand boils on the north side of that deposit. And it points out that sand boils and water ejecta don't have to come up straight over from what liquefied, but can move laterally depending on subsurface heterogeneities in the ground. And so the findings from Palinurus Road, the predictions of responses were consistent with different earthquake events with and without triggering of surface manifestations. We conclude that lower permeability C1 stratum on the south side, which is a stratigraphic heterogeneity, that's why pore pressures diffuse by horizontal seepage to the north. We get more water flux on the north side, and that would be why you accentuate and see boils on the north side, but not on the south side. And the key is that doesn't mean you didn't trigger liquefaction on the south side. It just meant that's not where the water came to the surface. And simplified procedures, 1D procedures, of which we've developed a number over the years, they're not able to explain those differences. They're still good and useful procedures, but the simplification and the ease of their use comes at a cost. Here you need to model the dynamics and diffusion to see that process. I had 2 others. Wu Feng I should jump through these quickly. It's just a lateral spread from Taiwan. It's in a rice field. You see the ground cracking, and there's an old channel here, or a river, kind of channelized feature. The equipment here is digging out the lining and repairing the site and reestablishing it. And this was a site that Daniel Chu, Jonathan Stewart, and others documented, and all the data is in the peer website. So we source that data. The site is an area of interlayered overbank deposits. And so when you look at the profile, we have a lot of overbank silty sands and silty materials. So the blue here are these plastic silts. The green is the interbedded silty sands. The yellow are cleaner channel sand deposits that come from the meandering of the canal channel. So you get periodic channel fill sands. The upper unit, the upper 5 meters, is slightly younger, and it has slightly lower strengths and densities than the same lithological features in the lower part of the unit. So we generate stochastic models for these. In this case, we did 3-dimensional ones. And the point I wanted to make here is we have a lot of CPT data from Daniel Chu and Stewart's work, but it's still not enough to constrain the stochastic models. And here, you see this yellow layer here is an easy one to point out. This is in the direction of, that layer is continuous in the direction of the channel, but it's not continuous in this direction. And that's because you have to constrain it by understanding the direction of water flow. Features will be more correlated up and downstream than they are cross-channel. And you need that kind of geologic model insight to run these types of stochastic models. We then cut 2D sections. We run FLAC models. This is the summarized to show that predictions of displacement, lateral ground displacement versus distance from the channel. There's the channel. The red zone is what you get from summing ground cracks, and you see 1 to 2 meters of movement at the channel. The different solid lines are from different realizations and different stochastic models. In general, we predict everything from 60 centimeters to almost 2 meters. You generally get on the range of the observed displacements at the channel slope, maybe a bit less. You're doing okay, 10 to 20 meters, but all the analysis models were over predicting displacements further from the channel. This might be because we're doing 2-dimensional models and 3D might work better. It might also be because continuum models don't do cracking and graben formation very well. So there's a number of things we might not be doing well, but at least we're on the conservative side in this case. So the findings here that generally the displacements envelope what was observed, over predicting movements further from the channel. The lithological variability in these models, this was modeled using transition probability indicator geostatistics like we used before. And again, you had to have a geologic model to interpret the data. We point out the near channel deformations are really governed by the details of the canal lining, which are poorly known. And so that's an epistemic uncertainty here. We just don't know the data. And that in the end, these kind of stratigraphic uncertainties plus the non-stationary trends of fines caught to another, these were more impactful than the variability between realizations. So getting the key strata was more important. 1D simplified methods, again, could not predict the differences in these patterns. One more was Wynn Avenue. This is a different case history in that it's relatively modest movements. It comes from the Northridge earthquake. And along this roadway, there's just a small feature here where the ground settlements were only about 10 to 20 centimeters over a distance of about 12 meters. It's like a little graben. Now, we want to see if we can predict small movements as well as large. So this interested us. It's also important to note that this kind of movement is enough to break water distribution mains and trunk lines in the area. So the water utility districts, water providers, were interested in predicting where you get this amount of movement because it damages your utility systems. We're in an area where we have alluvial fan sediments come off the hillside, as well as you get these sheet flood deposits and then stream channels that they're ephemeral. They come and go and they evolve on top. So things move laterally, and I'll show you why that's important in a second. This is the cross section. It comes from work by Tom Holzer and Michael Bennett, the USGS. We source all their data, and they are very, very generous in sharing it. This lower unit C is a clay. It's not going to be our problem. The problem layer is this layer C1 in yellow. They map this layer as the problem layer for liquefaction in the Northridge earthquake. And this upper layer here is a clay layer where it's below the water table. It's actually weaker in this range. And so the undrained strength of this clay layer is important too. This hatch zone right here is called the graben. This is where the ground settlement was occurred. And downslope of it, things were moving a little bit downhill. Now, when we look at this model, they wanted to understand why the graben was there. So in this zone, they did a very dense array of additional CPTs. And if you took these individual CPTs close, you see lots of yellow, which is from the CPT maps to clean sands. And then down here, it turns to a lot of green, which maps to silty sands. And there's a significant difference in these are looser, siltier materials, and these are cleaner, denser materials. That happens right about here. So in that zone, we are going to split this into two units, a C1A and B, and we call that a stratigraphic break. And in discussing with Tom Holzer, he agreed that that would be a better interpretation, and this can come from that kind of ephemeral valsing of the stream channels. I'm going to split that. We're going to do 3 analysis models. The first one is, they're going to be just uniform analysis models. We'll break layer C1A and C1B into their own zones. There's no inherent variability in this, just stratigraphic uniform models. Then we're going to do a stochastic model where in these subzones, we're going to put in the stochastic variability in CPT tip resistance, as well as undrained strength of the clays. And then this is showing the variability in the undrained strength of clay along the alignment of the road. This is a variability in the predicted cone tip resistance. The gray lines are the realizations. The black line is kind of the one realization to flag it out for you. The purple dots are from the CPT data averaged in columns. You see very little variability in this location because that's where they had a lot of CPTs. And if you have a lot of CPTs, you know the properties and you don't have a lot of uncertainty. Up here, there's a lot of variability because there aren't any CPTs. And when you don't have CPTs, you have more uncertainty in properties. And we did a third version where we just pretended we couldn't tell the difference between C1A and B, the clean sands and silty sands. We threw them in one hopper to see if statistics would save you. And the punchline is no. Math won't save you. You have to get the geology right. So we run these stochastic and uniform models in FLAC, PM for sand and silt, and this is our model shown here on the bottom. One result, top figure is showing maximum shear strains for the Northridge earthquake. Bottom one is excess pore pressure ratio. This is with a stochastic realization where C1A are the silty sands. They're looser, and you see they trigger high pore pressures and shear strains. C1B is the cleaner, denser sands. You get zones that don't trigger 100% pore pressure ratio, so they don't develop as much shear strains, and so this portion doesn't move, this portion does. That means if you plot horizontal displacement, this block of ground moved downslope about 38 centimeters, which means, and the upstream slope didn't move, which means if this doesn't move and that does, you get a graben here and you get a settlement of about 9 centimeters. So a little less than we actually observed. That's plotted here in terms of horizontal ground displacement and vertical ground displacement versus position. The red hatch is where the graben was observed. You see we predict horizontal displacements on the downslope side, very little on the upslope side, and you're going to get the difference occurring there, and that's why you get a down drop right out past it. The blue line here is the uniform model with no stochastic variability, and it predicts a sharper transition in movements and therefore slightly greater settlements of about 14 centimeters. And that's actually right in the middle of the observed 10 to 20. The uniform model actually did the best. And we did one where we grouped the materials and just saw like, could statistics take the silty sand and sand together? And the answer is no, that smears the behavior and doesn't predict the concentration of deformations. So our punchline on Wynn Avenue, and we're almost at the conclusion here, is that We basically got very similar results whether we did a uniform analysis model or if we did stochastic models. And what that tells us is the inherent variability isn't as important as getting the stratigraphic details right. The most important detail was knowing silty sands and the clean, denser sands were different. Simplified procedures did not pick up on these differences, so you couldn't predict that kind of concentrated loading that would go on utilities. And a little long, so I'm going to jump into conclusions. So thanks for bearing with me. Going through this talk was going over the idea that subsurface heterogeneities, when we're talking at the project scale, for practical purposes, we break them in three categories: stratigraphic, lithological, and inherent. So those are the three that we look at. Stratigraphic heterogeneity, we see over and over and again, it has a first order effect on the extent, pattern, and severity of manifestations. We see it in case histories, we see it in nonlinear dynamic analyses, and I just showed you some examples today. So you got to get the stratigraphic details right. When it comes to lithological heterogeneity, they pose their own challenges. One of the biggest ones is it complicates site characterization whenever the interlayers are thin relative to our in situ tests. And that's an area that needs more research. The composite response of these deposits is really going to depend on how interconnected the interlayers are over the scale of the mechanisms that affect our structure and the strength of the respective interlayers. And we gave some examples and scenario studies to kind of illustrate those issues. Inherent variability. Here, scenario studies gave us some guidance on how to pick uniform analysis properties. Once you've identified major strata units and you don't have any systemic or systematic variations with depth or lateral, everything appears random, then developing a cumulative percentile and using something like the 45th to 50th percentile tends to give us unbiased estimates for the median displacements. 30th percentile gives us something more conservative. And then you have to recognize when the structures get small that the variability in displacements gets much larger. You have to allow for that in your evaluations. And the influence of inherent variability was illustrated by a number of examples that we went through. I want to make the pitch again. Geologic models are really essential to understand for depositional, the anthropogenic, and the environmental processes. Having a geologic model in mind allows you to better design your site investigation, interpret your data, decide how you want to represent that heterogeneity in your analyses, and it helps you evaluate the potential that you might have missed a liquefiable feature, which can be important if your explorations are sparsely spaced. We then move to NDAs for infrastructure projects. Here I want to point out that when you look at applying these types of more advanced tools, the uncertainties that you have to deal with, they include the subsurface characterization, the soil properties, the input motions, but they also include your modeling procedures. And so it's very important that the person running these models pay attention to good industry practices for performing nonlinear dynamic analyses, documenting the results, and getting them reviewed. In the end, the relative benefits of doing a stochastic model versus a deterministic model, it really depends on how they contribute to the total uncertainty in the computed performance and how that would influence your decisions. There's a lot of cases where it's not necessary to look at stochastic properties to reach a good engineering decision, but there are other times it could be very valuable for you. And so lastly, just emphasizing that the quality of any liquefaction study really depends on getting the site characterization done well and understanding the effects of subsurface heterogeneities. And these different analyses and cases we went over have all been attempts at trying to elaborate and learn a little bit about how heterogeneities affect us. And with that, just again, repeat, thanks. Co-author on the paper was Patrick. Lots of colleagues and friends have contributed through comments and discussions over the year. And a lot of the work that I showed were funded by our National Science Foundation and our State Department of Water Resources. I do appreciate you hanging in with me. With that, I'd be happy to answer any questions. And I'll pop out. How do I get out of stop share?
Thank you,
stop
Professor
share.
Boulanger.
There we go.
Yeah. Thank you, Professor Boulanger, for such an insightful lecture. We have few
Sorry
queries
for
from the
going real long.
we have few queries from the participants, and the first query is from Professor Ritesh Kumar. Professor Ritesh Kumar, if you hear me, you can unmute yourself and ask your query.
So, hi, Rose. How are you? Good evening.
Good.
Morning.
Yourself? It's good to see you.
Yeah, good to see you too. So thank you so much for such a insightful talk. I was just wondering, when we talk about the stochastic NDS analysis, right? One of the biggest concern is to map the scale of fluctuation, especially the horizontal one, because our CPTs are quite far apart. So when you randomize the field, how did you map the site-specific scale of fluctuation? If you could
so
give
it's
some more insights.
It's an excellent question. You know, at this point, I'll take the opportunity to plug the part on Paris Dam that I was not able to talk about. Is a great example. It's an embankment in Southern California where we worked with our colleagues in trying to apply these tools at scale on a major infrastructure project. Now, what you pointed out is that you almost never have enough data
True.
to develop the variograms and other details you need to define some of the stochastic properties. Almost never. And for that reason, you end up with certain uncertainty. So like the variograms in the vertical direction are easy because you're going to have CPTs and there are lots of data. So you'll develop your vertical variograms, no problem. But the horizontal variograms are very complicated because you'll never have enough data to constrain both upstream and downstream. So, X and Y in plan view. And they might not be stationary in that you might think you're in the same geology, but the stream meandered more over here than it did over there, and you haven't picked it up in your exploration. So you may not be picking up a quote non-stationary feature. And so part of it is the geology tells you a little bit about, well, how wrong could you be?
True.
And so you have with a good engineering geologist, you can talk through it and say, here's my variogram for horizontal correlation in these two different distances. What's the scale of the river meander? How big was that river feature? How big might it have been in the past? Do we have any geologic constraints? And then you might decide that, I don't really know this number. And the best thing about numerical models is the ability to parameterize your results. So you go, maybe that correlation is 50 meters, but maybe it's 250 meters.
Exactly.
Okay, and so you parameterize what you don't understand, being appropriately generous and humble on how well we define these. And what's interesting is sometimes the analysis models show you that some of these parameters don't matter much.
True.
And what can sometimes happen is, depending on the scale of your structure and the feature and what you're looking at, one of the biggest amounts is the percentage of material. So if you're in lithological, it's how much sand do you have that could liquefy versus clays and other things. You get that pretty good. For the average you get from the CPT's vertical, you get that number pretty good. The correlation length, what happens is if you say that they correlate really well, like 200 meters long, then for the same percentage sand in a unit, if they're really long and continuous, you get fewer of them. If you say they're short, you get more of them.
Exactly.
And they surprisingly tend to offset each other a little bit, as long as they don't get to where they're really, really large relative to the structure. So I think it's a great question. We could go on and on about that with different things, but the bottom line is a little humility on how well we do or don't define these, geology to constrain you, and then you have to have enough budget and time in doing these nonlinear dynamic analysis to parametrically examine what matters.
Thank you so much. Always lovely to interact with you. Thank you so much.
Nice to see you again.
Okay, so the other query is from Professor Anil Basgan. Please unmute yourself and go ahead.
Yeah, so good morning, Boulanger. So
Good morning.
these days, the imaging techniques are so much helpful to profile the ground completely and its variation. So I have seen most of your studies; those are not used. Or so, can you comment about that?
Oh, yeah. Can you say the question and make sure you're saying, are these tools used on projects?
These days, the imaging techniques, the geophysics methods are used to map up to 100 feet effectively, where you can understand the spatial variability and model that in the effective way. So I found that most of your cases only limited to CPT investigations.
Yeah. Okay, I think I have your question. Let me know if I answer it right. So there's two parts I would say. So in our practice, and I think certainly in North America, and in many countries, I think to try to answer your question, we have to break out kind of the business sectors a little bit, in that there are, say, commercial developments and buildings, and then we might have levees, long lengths but not a lot of money, and then you go to dams where you have more money and more time to look at them, big tailings impoundments facility, big infrastructure projects. And so as you go from smaller projects to bigger projects, we're always just adding tools to help us make better decisions. Smaller projects tend to just use simplified procedures, CPT based, SPT based. They're often one-dimensional calculations. Right? You put them in a spreadsheet or use programs like CLIC or others. They're just integrating strains or something with depth. And these tools are very useful, and they can lead you to good engineering decisions, but you need to take them with a grain of salt and understand their limitations. They will tend to overpredict deformations when deposits get thick. They tend to overestimate both settlements and lateral spreading, thick units, because they don't get the dynamic response characteristics. You don't get to predict the variability in movements or the interaction with buried structures, things like that. So they have limitations, but you can still use them to make good engineering choices, recognizing those limitations. When we move up to bigger and bigger infrastructure, every project I've worked on for the last 25 years has involved a nonlinear dynamic analysis. And so once you move up to dams, larger infrastructure projects, everyone can do a nonlinear dynamic analysis now. And what we've really been working on is getting more consistent good practices in the use of these tools. And so those tools become increasingly common and relatively
clearly. I think we are not in the same line. See, the question is that, so I do agree that the spatial variability is very important for nonlinear modeling. The question is that the technology used was only limited to, again, the CPT-based procedure, rather the geophysical imaging techniques, which is more representative to get a spatial variability.
Okay, so I think maybe I didn't understand the question, right? But so once you try to move up to modeling the subsurface heterogeneity, for any of the simplified methods you're going to use it, the CPT is way better. It's one of our best tools. It is our best tool for getting good stratigraphic details in geologic settings that you can use it in, and where you can use it, you can get a really good sense of the subsurface stratigraphy, and it can give you a good sense of the variability across the site. So in terms of mapping out your stratigraphic heterogeneity and understanding the variability in deformations, CPT is much better. The geophysics tend to smear over larger volumes, and then you miss those details. And they're also not really sensitive to the subtleties of differences in tip resistance or texture of materials. So geophysics, very important, but don't give you the details for geologic interpretation as the CPT does. In terms of explicitly modeling the subsurface uncertainty, the geostatistics in it, we rarely see that in practice. There are, on larger projects, every once in a while, there are people who have developed the skills and techniques in-house and have applied stochastic models on certain projects. It's not real common, but it has been done. And sometimes, you know, the conclusion is it didn't really help much. And the biggest things were getting the geology right, the seismic loading, the uncertainty in the ground motions, and doing the analyses right. That if you did those, the uncertainty in the properties and the earthquake often were bigger than the uncertainty in the variability in the ground, such that the stochastic modeling often didn't change the larger decision that the owner has to make. You know, like fix a site, not fix a site, modify. Where it sometimes gave valuable insights and has proven very handy was when you had long infrastructure and you were trying to understand the possibility that, say, along a water supply tunnel or some major long utility corridor pipeline, how the variations and movements along a facility could cause local damage. That's really where I've seen it have a lot of use.
Yeah, thank you.
You're welcome.
Okay, so another query is from Saurabh Gupta.
Hi, Ross. This is
Hi.
Saurabh. I actually represent the investigation side of the business. So I was listening to your conversation now. I completely agree. I'm a big fan of CPT myself, and I think it is the best tool that we have. My question is, for a simplified one-dimensional liquefaction triggering analysis, what we have found is that the cyclic resistance ratio from CPT is simply not matching what I get from a simple analysis, you know, sort of from NCR summary report, what we get from say N60 values. So
Okay.
and the difference is huge. It's not like a 5-10%. The difference is, you know, the CRR values from CPT is often can be as little as 50% of what I get from N60 values. I'm seeing this across all kinds of sites. So I'm talking about data spanning like thousands of CPTs and boreholes at the same site. And so I have found, I think from UC Davis, some papers which suggest that you guys are having a similar observation. I just wanted to double check that with you in person.
Yeah. I mean, it's a great question.
We are stuck. We don't know what to tell the customers. End of the day, what do we believe?
Yeah. So we've seen differences that have, you know, sometimes aren't large in the types of soils, and when we tend to be in cleaner sands, we haven't seen really large differences, which is the correlations were developed to be consistent for cleaner sands, and generally when we haven't seen where we've seen larger differences with sands have been where we've identified problems with energy transfer and SPTs. So at large depths, energy losses and borehole at large.
I'm doing now, so I agree. So we are using now automatic SPTs and we are doing SPT energy measurements on all our sites. So we're correcting back to N60. We're trying to do all the right things.
Yep. So you're doing the right thing there. So that makes sense.
But it doesn't match.
No, you know, where we've seen the biggest differences come in are when you get into slightly silty sands with a little bit of plasticity, the CPT tip resistance comes down rapidly. So a modest amount of plastic fines. You might log the material as a silty sand, but the silt has got just a little bit of low plasticity to it. And the tip resistance in the CPT comes down much quicker than it does in the SPT. So I don't know if that maps with your experiences, but I've seen bigger differences once we get into those.
Big differences in clean sands, dirty sands, all kinds of stuff. And consistently over many years now. I saw a paper by, I think, Professor Emeritus, which suggested similar differences. So this is something I was very keen to. And huge differences. So the shear wave velocity based liquefaction analysis matches what we get from the CPT, and that's encouraging. Right? But the SPT based analysis is just off. It's off the charts. So if I plot the CRR versus depth, what I get from SPT analysis is just the values are double of what I get from CPT and shear wave velocity, and that's a big concern.
Well, that is very good information, for us. We're gonna have.
If you allow me, I will email you some of the data, and maybe we can take this up one-on-one. I would. Okay. Thank you so much. Thank you.
Thank you.
Another query is from Satish Sharma. Just unmute yourself and ask the query, sir.
Hello. Oh, I think you're muted, or I'm not hearing you.
Sir, you just unmute yourself. We cannot hear you.
Oh, his microphone is not working.
You can read the question.
Am I audible now?
Now, not well. I can hear you now.
It's a general question.
Sir, just repeat your question, please.
You can read the questions. These questions are given, no?
Okay. Professor Boulanger, I am just reading the question from Satish Sharma. The question is, what is the status of prediction of parameters of earthquakes, particularly the timing and magnitude, and what is the reliability of such predictions?
Predicting the timing and magnitude of earthquakes.
Yes.
Oh, that's a seismology question. But so if you're talking about timing, the prediction of earthquake occurrence, that's not something we do well. There are ground motion models that are better able at predicting when you have higher and higher probabilities of an event in the near term, the next decade or so. And those models are getting better, but the ability to predict the actual timing of an earthquake event is still poor and not really given a lot of credence in certainly North American practice. I think people would still like to try to figure out how to do it, but it's not there. In terms of the magnitude, the ability to predict the magnitude, and here you have to think about the recurrence relationship for a given fault source. You have a distribution of possible magnitudes, and the different magnitudes all have their different recurrence. Those models have gotten better over the years, including allowing for recurrence models allow for characteristic faults that like to have a certain set of magnitudes versus distributions that truncate, truncated distributions, other kinds of variations on those distribution. So when you say the magnitude, you have to think of the distribution of the different magnitudes and their recurrence. And all of those really depend on the quality of, well, the geologic understanding of the fault characteristics and its distribution. We still have problems even in well-developed and well-studied areas of knowing whether fault strands are connected or not connected, whether they can step over or not step over. And so predicting the magnitudes, in general, we do pretty well at it. But if you're asking about the finer details, there are still cases where it is challenging to know the magnitude distributions on complex fault sequences where you're not sure if they are connected strands or not. I'm not sure that answered the question. We're getting better at the magnitudes. Timing has never been very good at.
Thank you, sir.
You're welcome.
Okay, that was the last query from our participant. So as we come to the conclusion of the lecture series on engineering the future progressive practices in geotechnical engineering, on behalf of the Civil Engineering Department and IJ Student Chapter at IIT Roorkee, I, Shweta Singh, extend my warm and heartfelt gratitude to our speaker, Professor Boulanger. His profound expertise and insightful contributions have greatly enriched our understanding in this field. I would also like to acknowledge the active participation of our audience today, and we are very thankful to the participants for holding their patience and extremely sorry for the delay. So thank you all once again. And in the last, I request everyone to open their camera so that we can have one group picture up for the today's session.
It's a great idea. And thank you again for the invitation and congratulations on such a successful student group.
Thank you so much. Thank you, everyone.
Thank you.